Okay, so let's look at the Fundamental Theorem of Calculus, Part 2. So FTC 2. All right, so we have this. If f is continuous on AB, and what else? Oh, that's it. Then we have the following. The integral from A to B now, so not an area function, but the actual region from A to B, a stagnant region, doesn't change, is equal to capital F of B minus capital F of A. All right, and then do you guys remember that notation we use? F is any antiderivative of F. All right, so kind of similar to the Fundamental Theorem of Calculus Part 1, where this is our area function, and if we took the derivative of the area function, it got us back to the integrand. Okay, so there you go. So let's look at a quick example, and then we're actually going to do a proof just to see how everything is related together. So let's say we are looking at the integral from 1 to 3 of x dx. According to our Fundamental Theorem of Calculus Part 2, this is f of 3 minus f of 1, okay? And we do this often, right? Whenever we evaluate integrals, we use this notation. So there's a shorthand way of writing this notation, and it's like this. We write f of x, so we find the general or just an antiderivative first, and then we say we're going to evaluate it from 1 to 3. All right, so this is new notation. I'll write that in there. So this is our new notation. And it means it's f of 3 minus f of 1. Okay? All right, so let's return to our problem. We have this area under the curve of x from 1 to 3. And we'll do the most basic antiderivative, because remember the definition says any. All right, and antiderivatives differ by a constant. So I'm just going to choose the antiderivative without a constant, because wouldn't that be easiest, just not having to deal with a constant? Okay, so what's the antiderivative of x? Well, remember we add one. It's a reverse process. So when we take the derivative, we subtract 1 from the exponent. So the antiderivative, we add 1, and then the coefficient is going to be 1 over the new exponent. So 1/2 x squared, or x squared over 2. And now we're going to evaluate that from 1 to 3. Okay, so that means, this is our new notation, we're going to be looking at 1/2 times 3 squared minus 1/2 times 1 squared. Okay, so what's that? 3 squared is 9 halves minus 1/2 is 8 halves, or 4. And there you go. So we were able to find this region without having to, look at areas or do 1/2 b times h, anything like that. We used the Fundamental Theorem of Calculus Part 2 to figure that out. That's very exciting, right? Also, if you guys remember when we were evaluating the integrals, we also used like the limit definition and then summation notation, and it was a headache and it involved a lot of paper. Let's go back to that one we calculated, right, to be, was it negative 3/8? Or negative 8/3. Now we have the Fundamental Theorem of Calculus. Let's think of the antiderivative to that function. So what's the antiderivative of x squared? Well, let's see. The new exponent would be x to the 3rd times 1 over 3. And then let's see, minus 3 times x. So the new exponent would be 2. And then that would be the new denominator, right? 1/2. And then we multiply by 3. And we can always check, because it's always nice to know how to check. We can take derivative to check. Because remember, these are reverse processes. Derivative to check. All right, and that's an optional step. Okay, good. And now that's our antiderivative, and we're going to evaluate it from 0 to 4. 0 to 4. Okay, so we're going to plug in the 4 first, and then we're going to plug in the 0, and we're going to subtract them. Okay, so 4 cubed minus 3/2 x squared becomes 3/2 4 squared. Minus, oh, I love plugging in zeros like this. Just that whole thing will become 0 when we plug in a 0. Okay, so 4 cubed is 64. And this is going to be 3 times 16. 3 times 16 is 48 over 2. Okay, and then, however you want to do that, you can throw it in a calculator, something like that. But we're going to get negative 8/3. All right, and if you didn't have a calculator, we could definitely do it without a calculator, right? 48 over 2 is the same as 24. And then, you can multiply top and bottom by 3. Okay, something like that. Okay, so there you go. I'll keep going. 24 times 3 is 72 over 3. And that's how we're getting the negative 8/3. All right, so that was all the itty bitty steps. Okay, so there's your Fundamental Theorem of Calculus part 2. So now we have an easy way of evaluating these integrals. Because remember, it was quite difficult, right? We had to do all our summation, notation, laws, and then we had to take the limit, and then we finally found it. So if the instructions do not say to use the definition of integral, you guys can use the Fundamental Theorem of Calculus, and it's much easier. All right, let's prove this bad boy. Proof of the Fundamental Theorem of Calculus part 2. Okay, so let's use the Fundamental Theorem of Calculus part 1 to help us. Let's bring in our area function. Okay, and so we know by the Fundamental Theorem of Calculus part 1 that this derivative is going to be f of x. So the derivative of the area is f of x. Okay. Let's say there's another antiderivative. If f is another antiderivative, remember, antiderivatives differ by a constant. So that means f would have to just differ by a constant from g. Okay? That's what we know about antiderivatives. Okay, so I want to talk about, because I'm just going to go back to the Fundamental Theorem of Calculus, we're going to have to somehow show that this expression is equal to f of b minus f of a. All right, so let's introduce f of b minus f of a, okay, because we just said f is any antiderivative of f. All right, so we have all these components going on in our proof right now. Okay, so then f of b minus f of a will be equal to, let's see, g of b plus c minus g of a plus c. Okay, and then the c's are going to cancel. So this is going to equal g of b minus g of a. All right, and let's do a little work off to the side. G of a, let's go back up here. If we were to plug in a, that means the upper limit will be a. Well, what's the integral from a to a? 0. All right, so we know that's 0, so that's going to go away. And then g of b, so that means now the upper limit is no longer x, but it's b, is that. Okay? And then that's that. We're done. Can you believe it? So now we have that f of b minus f of a is equal to g of b, but g of b is this. So here's g of b, and it's equal to f of b minus f of a. And we're all done. So pretty good, right? Okay, so let's look at more examples using the Fundamental Theorem of Calculus, part 2. All right, so we're going to evaluate. So that could be an instruction when finding the integral. And remember, if it doesn't particularly say, use your sum rules, take the limit, or use the limit definition. If it just says evaluate, you're more than welcome to use the easiest way possible, which is the Fundamental Theorem of Calculus, part 2. Okay, so what's this antiderivative? That's kind of hard to find out. What might be easier is if we distribute that root t, get rid of the product, right? Because it's, remember how difficult it is to take the derivative of a product. You have to use the product rule. That's a headache. So rather, I'm going to distribute the root t, or t to the 1/2, right? So it's a strategy. And then t times t to the 1/2, that's going to be t to the 3/2. And now that antiderivative is much easier to find. One plus 1/2 is 3/2. Okay. So this is going to be equal to an antiderivative, whatever it is, evaluated from 0 to 4. So let's see what that antiderivative is. So let's add 1 to the exponent. So that's going to be 1/2 plus 1 is 3/2. Okay, and then multiply by the reciprocal of that new exponent, 2/3. And then don't forget the 4. Okay, and now next, minus t, to find the antiderivative as 1. So 3/2 plus 1, 3/2 plus 2/2 is 5/2. And the new okay, so let's clean it up. 4 times 2 is 8. Okay, so let's plug in 4 first. Okay, and then we subtract the lower limit of integration. It's 0. And again, this is lovely. It just so happens to be 0. So that helps. And remember when you're taking, if it's been a while since you've taken fractional exponents, remember how we do 4 to the 3/2 is we break up the 3/2 as a product of the numerator. So root so we're going to take the square root of 4 first, then raise it to the 5th power. Let's see, 2, 4, 8, 16, 32. Minus 0. 4/3 minus, let's see, this equals 16 and 16. Oh, goodness gracious. I stopped. Okay. Sorry about that. And we're no longer. Is now 64. There on the exam, that'd be fine. We can also, find the common. Oh, so using the fundamental theorem of calculus, it's kind of nice, right? Okay, so let's look at some special cases. So let's say we wanted to evaluate a function from -2 to 2 of 1 over x squared dx. Over x squared is a negative exponent. And then, find the antiderivative, evaluate it from -2 to 2. Let's see, if we add 1 to -2, we get -1. So negative x to -1. And then we'll plug in the 2. And then we'll plug in the -2. Gosh, that's a lot of negatives. 1, 2, let's see, minus -1 over -2. So okay, so it looks like it does not exist. The function is discontinuous. So we can't use the fundamental theorem of calculus. Okay. If it happened to be the integral from, 1 to 2, that's okay. It's the fact that it's discontinuous on the interval that we're asking, on -2 to 2. That's why we can't do it, because it's on that particular interval. Let me show you another example of this function, but the integral does exist, even though the function is continuous. And we'll see what the difference is. So we're going to define our function f to be the following. It's going to be a piecewise function. So it's going to be 2 if x is between -2 and 0, endpoints included, and then we're going to leap up to 4 minus x squared if x is between 0 and 2. Okay, so let's sketch it out really quick. All right, so we're saying from -2 to 0, we're the constant function 2. So -2 to 0, endpoints included, we're the constant function 2. And then we're 4 minus x squared. Okay, so remember, -x squared is an upside down happy face, and 4 means we are going up 4 units. Okay, so when x is 0, When x is 0, that's where we start. X equals 0, it's going to be 4. Open circle, right? And now we're just going to be an upside down parabola. And we're going to end at 2. And notice if we were to plug in 2, 4 minus 2 squared is 0. Okay, so something like this. So we're going to think of this problem like this. We're going to think of it for negative of f of x, and that is going to be 2. And then we're going to add a chunk from 0 to 2, and from 0 to 2, that's minus x. Okay. All right, and then at that point, same thing. We find the antiderivative, and then we evaluate the function. Okay, so that there. We'll just leave that. You guys can try some more complicated examples because we've done examples like this, right? We're just going to evaluate this and then add it to this one after we evaluate. But I want you guys to try some integrals on your own. Evaluate the integral. And remember, if it doesn't tell you how to evaluate the integral, the easiest method, in this case, that would be the Fundamental Theorem of Calculus, Part 2. Okay, so the integral from 0 to 1 plus e to the x dx. All right, and then the integral from 1/2 to 1 over the square root of 2 of 4 over square root of 1 minus x squared dx. And then the third one, let's do the integral from -5 to 5 of e dx. All right, so go ahead and push pause and see how you do. All right. Let's start with that first one. So remember, e is a constant. So if e is in the exponent, this is behaving as like x squared, x to the 1/2, x to the e. So if we wanted to find the antiderivative, well, our rule is we add 1 to the exponent, and then the new coefficient is 1 over that exponent. Okay? And then the antiderivative of e to the x is e to the x. So that's the antiderivative, one of the antiderivatives, where we can do any. And we're going to evaluate that from 0 to 1. Okay, so let's do that down here. Just going to rewrite it. All right, so at 1, we're going to get 1 over e plus 1. X is equal to 1. So to the e plus 1 plus e to the first. Okay? And now we're going to subtract the 0. Minus 1 over e plus 1 times 0, lovely, plus e to the 0. And let's see what we get. So 1 to any power is 1. We're going to get 1 over e plus 1. E to the first is just e. Then minus 0. What's e to the 0? E to the 0 is 1. So then minus 1. And there you go. So that's number 1. Let's see how you guys did on number 2. Okay, so you can move this 4 outside if that helps. That's one of our integram properties. So what's the antiderivative of 1 over the square root of 1 minus x squared? Inverse sine. Because the derivative of the inverse sine is this. It's 1 over square root of 1 minus x squared. So that antiderivative is the inverse sine. And then don't forget about the 4. And we're going to evaluate that from 1/2 to 1 over root 2. Okay, and then this is disguised a little bit. If you clear that denominator, multiply top and bottom by root 2, you get root 2 over 2. Okay, so I'm just going to write that now. Okay, so this is going to be 4, and we'll worry about it at the end. So inverse sine of root 2 over 2, which is pi over 4, minus the inverse sine of 1/2, which is pi over 6. Okay, so we're looking at 4 times pi over 4 minus pi over 6. And then let's multiply through by 4, so the 4's cancel. We're looking at 4 minus 4 over 6 is 2/3, so 2 pi over 3. Okay, and we can combine this common denominator. So we're looking at pi over 3 for number 2. Pi over 3 for number 2. All right. And then the last one is integral from -5 to 5 of e. Well, remember, e is a constant. E is a constant. So you can approach this 2 different ways. You can use our property where it's constant times b minus a. All right, so plus plus, minus minus becomes plus, or 10e. Alternatively, what's the antiderivative of a constant? It's the constant times x. So another way we can do it. So this way that I did up here is using the integral properties. We can also use the Fundamental Theorem of Calculus Part 2. The antiderivative of e is e times x, because what's the derivative of this? Gets us back to e. All right, so this is using the Fundamental Theorem of Calculus. So plug in the 5, so e times 5 minus e times -5. All right, so again, 5e minus minus becomes plus, and we still get 10e. And again, it doesn't matter which way you do it because there's no directions, right? It doesn't tell you. So you can do the most efficient and easiest method. Okay, so those are the big theorems, the big concepts of this section. Over just some little details throughout the section, so kind of going back to some of the concepts we talked about previously. I want to go back to the Fundamental Theorem of Calculus Part 1 when we're finding derivatives of the area function. And we're not going to finish this problem, but we're just going to do the setup. Okay, and I'll show you why this is different because remember, g of x, normally the integral is from a constant to x. We also did constant to a function, but what if it's function to a function? We haven't done that yet. So let's just talk about our strategy and the setup, and we'll leave it at that. Well, we want a constant in there. So what we're going to do is we're going to introduce a constant so we can use the Fundamental Theorem of Calculus Part 1. So let's introduce a 0. So let's go 1 minus 2x to 0, t sine t dt, and then add the integral from 0 to 1 plus 2x. So that's one of our integral properties, right? We can look at a to c, was it, of f dx equals the integral from c to b of x dx. Whoops, I'm writing too fast. Is equal to the integral from a to b. All right, so we're just creating that midpoint. And the reason why we're doing that is because now we can use the Fundamental Theorem of Calculus part 1 because we needed a constant right there. And notice here, we don't have the constant in the lower integration. We have it in the upper. So what can we do? We can flip it. And when we flip it, what do we add? A negative sign. All right, so that's a strategy. And now that we have this, it's the same setup as before. So, you introduce a u, and you do the Fundamental Theorem of Calculus Part 1, and you use the chain rule. All right, so a concept we've already practiced before together. I'm going too fast again. There you go. I said u, I wrote u. It's not what I wanted to do. So then I'll just write etc. And I'll write that up here too. Sometimes with our notes, we want to make sure. Oh no, I'm good. Okay, etc. Okay, so there you go. So what else can we look at? Combining other concepts, because that's what we're doing right now. We're tying everything together because we're in the fundamental section. Let's say we have a function, f, and it's defined to be the area function of this function. And the question is, on what interval is f increasing? So we have to think back. So how can we figure out where f is increasing? Well, we look at the derivative, and it's where our derivative is what? Positive. That's the rate of change. So where the derivative is positive, that's where our function's increasing. Well, what's the derivative of f of x? The derivative is a direct application because we're going from 0 to x. So it's 1 minus x squared e to the x squared. So we have to figure out where this is positive, right? Where this function is positive. And how we do that is by finding the critical numbers first. It's defined everywhere, so we're just going to focus on the critical numbers. And we can solve this using the zero factor property. We have a product that equals 0, so it means the first factor can be 0, or the second factor can be 0. Okay? Well, if you remember, e to the x squared is never 0, right? Because e to the x never approaches the 0. There's an asymptote there. So that's never 0. So it has to be this one. So solving for x squared, or you can factor this too, however you want to do it. It's going to happen at x equals plus or minus 1. So 1 minus x squared, again, we have to figure out, those are the critical numbers. And now we can use the critical numbers to figure out if our derivative is positive or negative. Okay, here's our derivative. Remember, e to the x squared is always positive. Always positive. So if our function is going to be negative or positive, it's going to be determined by 1 minus x squared. Okay, so we can just really look at 1 minus x squared. And I know this graph looks like a parabola, and it's negative, so it's going to be a sad face. So it's going to do something like that, because we know that the zeros are plus or minus 1. So it's going to go negative, positive, negative. So we can do it quickly like that. If we don't see it like that, what's another way we can do to figure out where the derivative is positive or negative? Plug in your test points. Plug in -2 to 1 minus x squared. You're going to get -3. Plug in a 0, you're going to get positive 1. Plug in a 2, 1 minus 2 squared. You're going to get -3 again. Okay, so however you want to do it. But once we have that, what's the question? What are we doing, right? It's been so long. We want to know what interval is f increasing. Well, we ran the ID test, increasing, decreasing test, and f is increasing on that interval only, according to the ID test. All right, so we're combining those two concepts. Okay, let's do something else. So again, just a further application. Given that the cosine of x squared is greater than or equal to the cosine of x when x is between 0 and 1. Okay, so that's given. We don't have to prove it. They gave it to us. We're going to deduce the following. That the integral from 0 to pi over 6, and pi over 6 is less than 1, right? So we're in this interval, of cosine x squared dx is greater than or equal to 1/2. So we have to prove this, okay? All right, well, what do we know? We know that cosine of x squared is greater than or equal to cosine of x between 0 and 1. And we have a property that tells us that if a function is greater than another function, the integral is also greater than that function. All right, and again, we can do this because 0 to pi over 6 falls in this interval 0 to 1. I forgot my dx. Okay, let's evaluate this. Okay, and how are we going to evaluate that? Well, the antiderivative of cosine x is sine, because the derivative of sine is cosine. Remember, we can always go backwards. To find the antiderivative, we can check by finding the derivative. Make sure we get back to where we started. We're going to evaluate that from 0 to pi over 6, which is sine pi over 6 minus sine of 0, or 1/2 minus 0. And that's that. So we just showed that the expression on the left is greater than or equal to 1/2.